It's been a while since I did a nerd video, so let me correct that problem by throwing some math at you. When I was in high school, I learned that 0 factorial equals 1. It was given to me as a simple definition, and for a long time I assumed that's what it was. Sort of like how the square root of -1 is defined as I. But it turns out that it's actually very easy to prove why 0 factorial does equal 1. And in fact, while it raises some interesting questions about math, I honestly don't know why the proof isn't shown to students all that frequently. To go on a quick math rant, it's the fact that the interesting stuff like this is hidden from students that causes so many people to despise math, in my opinion. If they knew this sort of stuff existed... Okay, rant over for now. To demonstrate why 0 factorial is 1, we have to start with how a factorial is defined. The typical way is to think of an example. 5 factorial is the same thing as 5 times 4 times 3 times 2 times 1. So it's pretty easy to think of the general rule that any number, we'll call it n, when you do a factorial, it is the same thing as n times n minus 1 times n minus 2 times n minus 3, and so on. You subtract 1 from n each time until you finally get down to 1, and then you stop. Now this is okay as a general guideline, but it's a bit clunky to try to define it that way. The nice thing is that there's an underlying pattern that we can exploit here. We've looked at 5 factorial already, so let's look at 6 factorial and compare the two. If 5 factorial is 5 times 4 times 3 times 2 times 1, and we know from our pattern that 6 factorial is going to be 6 times 5 times 4 times 3 times 2 times 1, then what is the difference between 6 factorial and 5 factorial? Well, clearly 6 factorial contains all the same values that 5 factorial contains, but that's multiplied 6 times more. If you look at the end of the equations, these parts are identical. So with that in mind, we can actually rewrite our definition of what a factorial is with n factorial is equal to n times n minus 1 factorial. Thus, our definition of the next number in the factorial depends on previous numbers of factorials existing. Now, English majors might be immediately cringing at this so-called definition. After all, we are told in our English classes that you are not permitted to define a word by using the word itself in the definition. And that's what we just did here with math. Of course, this overlooks the fact that all words ultimately do become circular references in that synonyms merely point back to other synonyms which eventually will point back to themselves. But let's not get too pedantic here. The power in this form of a definition in mathematics, for the factorial in particular, is that it shows us the process is recursive. Now, recursive simply means that when you do a function, you feed the answer you get back into the same exact function and run it again, repeating that pattern again and again until a certain rule is met. And what is that rule? Well, we saw in the first one with the 5 times 4 times 3 times 2 times 1, you stop there. You do not go times 0. If you multiply everything by 0, you get 0. So in the case of factorials, our numbers all have to be positive. That means our process must always be able to give us values that are greater than 0. So let's kind of wrap all this up together. We have n factorial equals n times n minus 1 factorial. But we want to know what 0 factorial is. Well, at first glance, you might think that's really easy. We have n factorial on the left, so we can simply make n equals 0, and you plug it in, and you've got 0 factorial. So when we do plug that in, we have 0 factorial is equal to 0 times -1 factorial. And at this point, it would be really easy to just conclude that, well, -1 factorial doesn't matter because we're multiplying it by 0 anyway. So the whole number is going to be 0. 0 factorial is 0. But we just said it's actually 1. And that -1 factorial doesn't make any sense. It's like trying to divide by 0 in mathematics. It doesn't work correctly. So does that mean we actually have no value for 0 factorial? Well, on the contrary, we can actually rearrange this equation just a little bit and get an answer that is completely valid. After all, if we have n factorial is equal to n times n minus 1 factorial, well, what happens if we rewrite this in terms of n minus 1 factorial instead? To do that, we simply divide both sides by n. The n on the right cancels out, and that gives us n minus 1 factorial, and that tells us that n minus 1 factorial equals n factorial divided by n. And now you can immediately see why we can't set n equals 0 in this case, because we would be literally dividing by 0. But what happens if we set n to 1? So n equals 1. In that case, we would have 1 factorial divided by 1 is equal to 0 factorial. We have another definition for 0 factorial here. And in this case, we know any number divided by 1 is itself, once again. So this is the same thing as saying that 1 factorial is equal to 0 factorial. And we know what 1 factorial is, it's 1. So 0 factorial equals 1. Of course, given the fact that we now have two conflicting definitions of 0 factorial, one where 0 factorial equals 0 times negative 1 factorial, and the other where 0 factorial equals 1 factorial, the question remains, how do we know which is accurate, and can we even use either of them? Well, in this case, it's kind of easy to see if we look at some examples of other numbers. So we already looked at 5 factorial earlier in this video. Using the method here, where we can express this in terms of n minus 1 instead, we would have the following. 4 factorial equals 5 factorial divided by 5. And that is the same thing as 120 divided by 5, which is 24. 4 factorial is indeed 24. So let's just reduce everything by 1. 3 factorial would equal 4 factorial divided by 4. That's going to be the same thing as 24 divided by 4, which is 6. 3 factorial is indeed 6. So we do it again. 2 factorial equals 3 factorial divided by 3. That's the same thing as 6 divided by 3, which is 2. 2 factorial is indeed 2. And finally, we would have 1 factorial equals 2 factorial divided by 2. That's 2 divided by 2, which is 1. And 1 factorial is, as we already mentioned, 1. So if that same pattern holds, then 0 factorial is going to equal 1 factorial divided by 1. That gives us 1 again. So if this pattern fits, this is why 0 factorial is equal to 1. But what about that pesky alternate definition where 0 factorial equals 0 times negative 1 factorial? Well, we can continue the pattern we were just looking at and ask, what would negative 1 factorial be? So negative 1 factorial would be 0 factorial divided by 0. Divided by 0. We can't do that. What would negative 2 factorial be? Well, again, on the same pattern, negative 2 factorial is going to be negative 1 factorial divided by negative 1. But since negative 1 factorial is dividing by 0, we can't get a valid number in the numerator of that fraction. Thus, negative 1 factorial is itself undefined in mathematics, so negative 2 factorial would be undefined. If negative 2 factorial is undefined, then negative 3 factorial is, etc. So we're left with two definitions at this point, but one of them is a simple 0 factorial is equal to 1, and the other one is this really weird thing going on. It's saying 0 factorial is equal to 0 times some undefined thing, something not only undefined but impossible to define. Does that actually give us a contradiction within mathematics then? Well, not really. After all, since we have some undefined thing happening 0 times, the solution to 0 times undefined could very well be 1. We don't know. We also have no way of proving it one way or the other, since an undefined process is, by definition, impossible to comprehend. And therefore, that particular negative 1 factorial is not useful for mathematics. But the other solution that we got for 0 factorial is well defined, and it fits the pattern we see elsewhere. And there is no contradiction because we can't say what the undefined thing is going to do. Therefore, 0 factorial is indeed best understood as being equivalent to 1. And again, this is something that we can easily teach students at a high school level. This doesn't require you to know calculus. This doesn't require anything really advanced, super advanced. We can just deal with these issues, bringing up the fact that there are certain processes in mathematics that are undefined, and there are certain processes that can be done in two different ways, one of which is undefined, the other one is defined.